All right, so in the second half, we're going to talk a little bit about thermodynamics, and this is going to be very short. Some of you have seen all of this previously. If it's new to you, I promise it's easy, and I've got a Poggle packet that's going to link all the concepts together. Thermodynamics is going to look at the relationship between heat and work. We are going to link enthalpy, delta H, to entropy, a measure of disorder in the system, and free energy, the energy available to do work. When a process occurs without any assistance, we say that it's thermodynamically favorable. Now, most textbooks will say, oh, it's a spontaneous reaction. In the last couple years, the AP exam has gotten away from the term spontaneous and is using the term thermodynamically favorable. You'll see that on AP questions. However, the Poggle packet, I already ran it off, and it's hard to alter something that's copyrighted, says spontaneous. Spontaneous and thermodynamically favorable are synonymous, but you really want thermodynamically favorable, and you'll see it in my answer key.
Is that like decomposed hydrogen peroxide?
It occurs without any assistance. It's a spontaneous process, absolutely. Entropy is a measure of how energy is spread out among atoms and molecules of a system. Entropy is a measure of disorder in the system. Very backward concept. Free energy is what's going to relate the two terms together. When you have a thermodynamically favorable process, it's going to occur without any assistance. The reverse process then is not thermodynamically favorable. And here's the link between thermodynamics and kinetics. Is this reaction endo or exothermic? Exo. Here are your reactants, here are your products, here's the mid-region, the activation energy. So thermodynamics focuses only on the initial and the final, and kinetics is going to focus on the reaction pathway. So now you're able to link these concepts together. With entropy, what we're going to talk about is disorder in the system. And reactions tend to be more favorable when you go toward disorder. It's just like your room. It was neat on Sunday. I'm sure by today it's a complete disaster area. It's a natural process. When you go, for example, from a solid to a liquid and a liquid to a gas, you get more and more disorder. That's a good thing. That's positive entropy. It's a backward concept. Be careful there. The greater the number of particle configurations, the greater disorder. So if you have 4 molecules, for example, combined to one area, that's pretty orderly. But now look how many different possible arrangements you can have. The more arrangements you can have, the greater the disorder, the more likely you will have a thermodynamically favorable reaction. Entropy, like enthalpy, is a state function. It depends only on the beginning and the end. And these processes illustrate an increase in entropy, hence positive entropy, or going in that direction. The melting, you go from solid to liquid, you get more disorder. That's a good thing. That's an increase. Solids or liquids vaporizing to form gases, increase in entropy. Solids or liquids dissolving in a solvent, they're moving around more, increase in entropy. Chemical reaction producing an increase in the number of moles of molecules of gas. I'll get back to that one. That's trickier. When you heat a substance, the particles move faster. When you expand an ideal gas, so initially you're here only, you open the stopcock, you have greater disorder. So all of those show an increase. Let's take a look at these. Predict whether each of the following leads to an increase or decrease. So keep those rules in front of you and you'll be fine. You're going from gas particles to a solid. Is that getting more ordered? Yeah, so this is a decrease in entropy. you've got 2 moles of solid and you're generating solid and gas. Increase or decrease? Increase. Now this one's too close to call. This is one of those elections too close to call, something that you're going to look at the videotape of to review a play. When you have just gaseous particles, you need to look at the sum of the coefficients. So here you have 2 moles of gaseous reactant. Here you have 2 moles of gaseous product. This is one of those too close to call type situations. You would need a value there. Here you have all gases, but you have 2 moles of gaseous reactant, and you have 2 plus 3 moles. You have 2 plus 1 is 3 moles. So this gets back to babysitting. You want to babysit 2 kids or 3 kids? 2, it's easier. 3 kids, greater disorder. Everybody wants different dinner. Everybody has to go to the bathroom at the same time. It's just tough. There's disorder in the system there. So that's an increase. Backward concept. The more disorder, the increase in entropy. The more kids you throw in here, the bigger the zoo it's going to be. All right? The other thing I do want to make clear, because I'm not sure this is clear yet, these terms get really confused. So when you're talking about entropy, that's S. When you increase in entropy, you become more positive, if you will, or you increase in value. When you decrease in entropy, you tend to become negative. This is disorder. This is order. Just remember what Mom's saying now. Oh, I want to go date that 20-year-old guy. No. Negative order. No, no, no. Negative order. It wasn't that funny. All right. Don't confuse this with enthalpy. All right. Here you have H. Remember, positive is endothermic, negative is exothermic. Okay?
So, more disorder is endothermic?
No. No. And these are different concepts that we're going to link together. Just because you're exothermic doesn't mean you're disordered. Don't do that. Because what you're actually going to see is here's solid, here's liquid, here's gas, and we just established that if you go from solid to liquid to gas, what can you say about entropy? It's increasing entropy here, more and more positive. And in the reverse direction then, this is what happens when you get punished for going out with that 20-year-old. You're sitting in your room and you're vibrating. Oh my God, they're going to yell at me more. Please don't think about these things while you take the test. You'll start laughing hysterically. All right. Now, just remember.
Our mom was out with a
I thought, yeah, I thought you were saying my mom.
Yeah.
That's what I thought too.
weird.
No, I said you ask your mom.
Oh, see, I thought my mom was going out there.
That's why I thought it made sense with it going down because he's younger than her, so it's less.
As long as it works. As you go, just remember, solid to liquid is melting, and men, they'll melt your heart, right? Sometimes. Melting is endothermic. So in this direction, you've got endothermic. Delta H is positive. And in this direction, we have exothermic. Delta H is negative. And I've got a good joke for that, and I'll give it after the videotape is off. Not on the videotape. All right. Okay? Yes, yes? All right. So I think we will stop there. There were just a few terms that I wanted to make clear. Now, in this free energy packet, I want you to look at 1 through 10. For some of you, this will drive this home like crazy. For some of you, it will start to pull it together. I can't emphasize enough the importance of doing some problem solving prior to Friday. On Friday, we'll put the pieces together. We'll link enthalpy and entropy to free energy, spontaneity or thermodynamic favorability. All right?